Hello dear students, another problem about the this is equipotential lines or surfaces. Uh, so let me define what are the equipotential lines or equipotential surfaces first. Equipotential lines or equipotential surfaces are those lines or surfaces which has constant potential at every point. So the line or surface which has constant potential at every point. So in this question we have a certain region characterized by uniform electric field. Electric potential is measured along two equipotential lines. VA, the potential is VA along first line, that potential is 19.9 minus 19.9 millivolt. Potential VA is minus 19.9. It means at every point on this line the potential is constant, that is equal to minus 19.9. Similarly, we have second line B, where the potential is 55.6 millivolt, and at every point on this line the potential is constant, that is 55.6 millivolt. So the two potentials are minus 19.9 millivolt and potential 55.6 millivolt, and we have to determine the x component of electric field. So to find in this question we have to find electric x component of electric field E, x component of E. So as we know that along the x direction, along the x component, as we know that along the x direction, along the x component where the electric field E, and we know that there is no change along the x component. There is no change along x component of electric field intensity, because the electric field intensity can be determined by using the formula of potential gradient. E is equal to minus del V over del R. The rate of change of potential with respect to distance gives the electric field intensity, magnitude of electric field intensity. Mean del V or del T is the rate of change of potential, that gives us E, that gives us electric field intensity E, electric field intensity. So x component, as we know that Ex equal to minus del V x over del R x. So as we know that as we change the distance along x axis, the potential is constant. Any distance along change of distance along x axis along the same line, so that the component of Ex must be equal to 0. No change of potential along x direction. So if the no change of potential along x direction, so Ex equal to 0. Ex 0, whatever the distance R is, so that the change of potential is 0. So electric field intensity, the x component of electric field intensity is 0 along the x component. Okay, now for the same problem we have another question which has the same problem, two equipotential lines VA and VB. The potential is 5.8 and 52.6 millivolt. So VA is equal to 5.8 minus 5.8 millivolt, and the potential at B is 52.6 millivolt, and we need to determine the potential Y component of electric field intensity, EY. So in order to find EY, we use the formula del V of Y over del RY, del Vy and del divided by del Ry. So that we know that Ey is equal to del V. So the change of potential is Vb minus Va, and divided by the distance of the distance between V to B, del R between B to A. Okay, now we know that the del Vb is 52.6 millivolt minus Va is minus 5.8 millivolt. We divide with the del R. So del R, you can see that here del R is equal to, so this is absolute distance. Here we have minus 1, then we have the plus 2. So distance between minus 1 and plus 2 is 1, 2, 3. So here we have 3 centimeters. So del R is 3 centimeter. But the answer is in meter, so we get 0.03 meter. So delta R from B to A or A to B is 0.03 meter. So EY, electric component Y, electric field intensity Y component is equal to 52.6 minus into minus. This will give us plus. Minus minus gives a plus. 52.6 plus 5.8 milliwatt over 0.03. So when we solve this and we get answer in milli is 10 power minus 3. Okay, we convert this into 10 power minus 3. So finally when we convert this into minus 3, milli is 10 power minus 3 volt. So the final answer is 1.94 Newton per coulomb. So this is the Y component of the electric field intensity. So I repeat again, for the X component, we know that the X component is 0 because there is no change along the X potential of there is no change of potential along X direction, so that the electric field intensity along X direction is 0. So, and the change of potential along Y direction, we need the distance Y between VA and VB lines. Okay, this is absolute value. We don't need negative care of with the negative or plus. So this is the absolute distance from VA to VB, that is 3 centimeter. That is 0.03 meter. And the potential difference is final potential VB 52.6 and subtract with the initial potential, that is minus 5.8 millivolt. Okay. Then we convert milli into 10 power minus 3, so that we got answer in the SI, that is Newton per coulomb. Okay, thank you.